Yeah. Hello, everyone. My name is Onur. Today, me and Vanyu will speak to you about applications of large language models to improve contextual relevance at Pinterest. We will first discuss the relevance problem and challenges at Pinterest. We will cover teacher model-based knowledge distillation approaches utilized in the relevance teams and the LLM embedding-based features deployed in production. Finally, we'll talk about relevance labeling by utilizing ChatGPT. We will start with the relevance problem at Pinterest. The first question is, what is relevance? The textbook definition refers to the degree to which recommendations align with the user's query and intent. Here are examples for related pins recommendations and search ranking. In related pins, the context is the user's close-up pin. For the pin backyard patio seating, pins showing outdoor conversation sets would be relevant, while a pin showing clothing might be irrelevant to the original user intent. In search, the context is the user search query. For the query office desk, the office seating sets would be relevant to the query. However, a security system might be irrelevant. However, it is not often as trivial to quantify relevance. Take these two search queries as an example. For yellow background query, the first image is orange, while the third image example is only partially yellow. For the query board game room, would a dartboard or a PC game room be relevant, irrelevant, or partially relevant? Due to these, relevance is often defined multi-grade and requires extensive guidelines to measure for different contexts and contents. How do we control relevance in the search funnel? To collect the ground truth, we ask human labelers to rate search query and pin pairs on a scale of relevance. The data collected is used to train relevance models. These models are then utilized in retrieval, ranking, and utility parts of the search funnel. We have experimented with dropping relevance models from the search funnel. While this led to short-term wins on user engagement, we have observed drops in the long term, which proves the importance of relevance. One major challenge we have faced is the time and resource required to scale up the relevance labels. We observed that growing the relevance model size solely by the labels obtained from the crowd in fact led to overfitting and worse performance. To overcome this, we've utilized pre-training and knowledge distillation approaches, which would be covered next by Vanyu.
Thanks, Honor. Next, I'll share more about the teacher model and knowledge distillation process for the student model. On a high level, the knowledge distillation process looks like this. First, we use around 1 million human labels to fine-tune LLM to generate high-quality teacher model. Then, the fine-tuned teacher model is used to inference large volume of unlabeled data to generate augmented labels. And finally, the augmented labels are used to train the production student model. Through this process, we're able to scale the label volume from millions of rows to billions of rows. Next, let's take a closer look at the teacher model architecture. We have already mentioned LLM as the main component of the teacher model, and the raw text features are used as the inputs to the LLM. Besides the LLM, we also experimented with adding visual encoder that takes in image signals, as well as incorporating the student model architecture into the teacher. The student model contains additional query side feature, pin side feature, as well as query pin interaction features. To incorporate the visual signals, we have tried two main approaches. The first approach is to utilize the image-to-text models, such as Blip, to generate image captions from the image. Then we append the image caption to other text features, such as search query, title, descriptions, and URLs. The second approach is to use a visual encoder to extract visual features directly from raw images, and then combine with text features through a fusion model. We have seen improvements from both approaches, and we will share more results later. Next, let's look at some of these results. First of all, we have run benchmarking with various large language models using text features only on our own internal evaluation dataset. From the plot on the right, we can see as we scale up the language model from distilled bird to Roberta base to Roberta large, then to Roberta X large and Roberta XX large, the model performance continue to improve in terms of both AUC and the F1 score. By adding visual signals in addition to the text inputs, we can observe even further improvements through both the image caption method and the visual encoder method. The combination of the two methods give us the best results, as you can see it from the graph. In addition to the improvements we're seeing in the teacher model, we have also seen success in the knowledge distillation process from teacher to the student. Here in this graph, we can see that the student model size is kept constant and model performance still improves when pre-trained with more powerful teacher model, Roberta XX large compares to Roberta large. So this shows that the improvements in teacher model we're seeing through adopting more powerful LLMs can directly translate into the improvements in student model, which are served in production. Next, we'll discuss using LLM to generate embedding features. First, let's look at the generation process of the feature. We start with a Pinterest version of the LLM that is pre-trained generatively on all sorts of Pinterest text. And then we fine-tuned using relevance-specific human labels. After the fine-tuning, we use the fine-tuned LLM to generate text embeddings for pins and queries. To use the embeddings in the production model, we have concatenated the pin and the query text embedding through a small MLP layer, and then concat the output, which is the combined text embedding, with other features such as the sages and pin to interest, and then together we feed that into the production model. With the addition of LLM embeddings, we have observed another 1% PRAUC gain, which also translated to online relevance metrics improvements. Next, I'll pass to Honor to share more about the GPT labeling.
Next, I'll cover the labeling efforts with ChatGPT. Here's a high-level illustration of labeling with ChatGPT. The system takes in a system prompt, which contains description of the labeling task and a few short examples on what the output should look like, which are outside of the scope of the talk. The user prompt contains the search query, pin title, description, metadata, and image captions, which are generated by a Blip2 model from the image. The output contains the relevance label, the confidence in the label based on the information that's provided, and a detailed description about the label and the confidence. Here we provide some results on a benchmark dataset. Note that this project is work in progress, hence the results and the conclusion could change in the future. Here, we fix the prompts and only update the inputs and the model. We can see that utilizing blip2 captions, a larger model, and visual input from GPT-4V lead to significant improvements in the accuracy. And the accuracy is very close to human judgments. We're optimistic that we'll reach or exceed crowd labeling accuracy in the near future. In summary, relevance models were bottlenecked by human labeling capacity, which are expensive and time-consuming to scale. We have observed that distillation from teacher models that utilize LLMs and visual encoders enable us to grow and improve the production model. Also, labels powered by ChatGPT achieves accuracy close to human labels. The advances we have achieved so far are promising and will continue investing in this field. Finally, I'd like to thank the engineering teams at Pinterest and everyone that contributed to the projects. Thank you very much for your time in listening to the presentation, and now we'll be happy to take any questions that you may have.
Yeah, we have a question from Siddhar. Do you observe the gap between student and teacher model increase with the increase in teacher capacity? If yes, what kind of techniques are you looking into for efficient distillation? Do you want to take this one, Honor, or I can?
Yeah, you can take it.
Yeah. So I think in general, we're seeing the student model could learn pretty effectively from teacher model. The PRUC gap we observe is less than 1%. But as the teacher model becomes more powerful, the gap does indeed become larger. So we're also exploring other enhancement to the teacher model, such as adding the visual signals and other features to make the to make the student model also more powerful. Let's see. There's another question from Arush. How are the ChatGPT generated labels evaluated by humans, as they can be prone to hallucinations?
Yeah, that is a good point. Maybe I can take it. Take the question. So we we generate a QA data set, a golden data set that is labeled by specialists in this field that generate the guidelines. At the beginning, when I mentioned the relevance is multi-scale, and this is we create guidelines that will help the crowd evaluate this. And there are these specialists that create the guidelines, also create QA data sets. So we evaluate the accuracy of both GPT as well as the crowd labelers on this data set. So we are actually comparing the human labelers, the crowd, against the GPT. And there are definitely challenges in both the hallucination, the prompt, as well as the inputs. The input signals that we provide may not provide sufficient evidence for labeling. So based on the QA, we do the root cause analysis, and we're trying to improve the accuracy. But as I mentioned, this is a work in progress, so we're not going to cover the details about the prompt engineering.
Thanks, Honor. We have another question from Shardo. what have been the main challenges in scaling such LLM approaches at Pinterest for production and real time? Yeah, I think I can chime in for this one. I think if we want to serve the LLMs directly in production, then the infra costs and latency are definitely one of the challenges. But as which is, I guess, one of the motivation we went with the knowledge distillation process. At the same time, there's also a lot progress on the infra side to utilize GPU and such. So we'll continue to explore this method to compare with the distillation. All right. I think that's all the questions we have. Cool. Thanks, everyone. And hope you enjoy the rest of the day's contents.